In November of 1929, 12 transatlantic telegraph cables snapped, one after another, over 13 hours, in sequence, not from corrosion, not from a ship dragging an anchor across the wrong patch of seafloor, not from any storm, any malfunction, any surface event that operators at either end of the Atlantic could identify or explain. The cables simply stopped transmitting, each one at a recorded time, each one at a different location, each one deeper and further south than the one before it. For years, no one could say what happened. And here's the true part that sounds like the premise of a thriller. The answer was hiding in the timestamps. When scientists eventually laid the cable break times against a map, the pattern was unmistakable. The breaks hadn't occurred randomly. They had occurred in geographic sequence, northernmost cable first, southernmost last, separated by intervals of minutes to hours that corresponded precisely to the time it would take something traveling at nearly 100 kilometers per hour to cross the distance between them. Something had moved across nearly 4,000 meters of ocean floor at highway speed, in total darkness, under pressure that would compress a human body to nothing, and snapped steel telecommunications infrastructure the way a landslide erases a footpath. Not a wave, not a current, not an earthquake, a flow. A dense, sediment-loaded underwater cascade, something the seafloor generates on its own, from its own weight, its own instability, its own accumulated mass, moving like a storm front across the flattest, darkest, most remote terrain on the surface of this planet. The ocean floor doesn't just sit there. It moves, and when it moves, almost nothing in its path survives. So what is this thing? What physics creates it? What triggers it? What does it leave behind, and why does it matter to every person alive who uses the internet? Descend to 3,600 meters. You have passed through every zone we have visited in this series. The twilight zone at 400 meters, where light died and animals evolved bioluminescence as a replacement. The oxygen minimum zone at 1,700 meters, where the vampire squid drifts. The midnight zone at 2,200 meters, where dragonfish hunt with private wavelengths and anglerfish wait for prey to walk into a light. The levels where marine snow falls, where plastic now descends contaminated and permanent, where bone-eating worms dissolve the skeletons of whales. At 3,600 meters, you have arrived at the transition between the bathypelagic zone and the upper abyssal plain. The seafloor here is approaching. Not the imaginary featureless expanse that most mental models of the deep ocean produce. Not a smooth gray moonscape of undifferentiated sediment stretching to the horizon in every direction. The abyssal plain is flat, yes, the flattest large-scale terrain on Earth, but that flatness was not here by default. It was built. Pressure at this depth is approximately 360 atmospheres. The weight pressing against every surface in every direction is 360 times the weight of the entire atmosphere above sea level. Temperature is between 1 and 3 degrees Celsius, cold beyond what most organisms associate with water rather than ice. There is no light. There has never been light here from any source other than the organisms that generate their own. The closest surface current is kilometers above you. The closest tidal influence is a faint gravitational whisper. This should be one of the most geologically stable places on Earth. Deep, cold, still. Removed from the forces that drive geological activity at the surface, wind, rain, rivers, glaciers, tectonic surface exposure, it is not stable. Below you, embedded in the sediment, readable in drill cores, mapped by survey equipment that has scanned thousands of square kilometers of this terrain, is a geological archive of catastrophic events. Layers of coarser sediment sandwiched between finer layers, disrupted sequences, buried benthic communities. Evidence, repeated across millions of years of accumulated time, that this floor has been swept, buried, resurfaced, and restructured by forces that move faster than most people believe water can move when there is no visible current to explain it. The abyssal plain at 3,600 meters is not a resting place. It is the destination of a process that begins hundreds of kilometers away, on the continental shelves, in the accumulating weight of sediment that rivers have been delivering to the ocean's edges for as long as rivers have existed. Here is the physics, plainly stated. Rivers carry sediment. Every river, the Amazon, the Congo, the Mississippi, the Ganges, erodes its catchment basin, picks up particles ranging from fine clay to sand to gravel, and carries them downstream toward the sea. At the coastline, the river slows, the current drops, and the sediment drops with it. It accumulates on the continental shelf, the shallow underwater platform that extends from the coastline out to the continental slope, typically at depths of less than 200 meters before the seafloor plunges toward the abyss. The sediment builds up, layer by layer, year by year, decade by decade. At a certain point, triggered by an earthquake, by a storm that destabilizes the upper layers, by the sheer accumulated weight reaching a critical threshold, the sediment fails. The slope beneath it can no longer hold it. And when continental shelf sediment fails on a slope leading down to thousands of meters of open ocean, it does not simply slide and stop. It accelerates. As the sediment mobilizes, it mixes with the surrounding seawater. The mixture becomes denser than the water around it, a heavy, slurrying mass of particles suspended in fluid, heavier than the water it is displacing, gravity-driven, constrained by the seafloor below it and the weight of clear water above. It flows downslope the way all dense fluids flow through less dense ones, fast, following the gradient, picking up speed as the slope steepens, incorporating more loose sediment as it moves, becoming more concentrated, more powerful, more destructive with every kilometer it travels. This is a turbidity current. The name comes from turbidity, a measure of how much suspended material clouds a fluid. At full intensity, the leading head of a turbidity current is so loaded with sediment that it is effectively a slurry rather than a water column. It is not transparent. It scours the seafloor it travels over. It strips loose material from the surface and adds it to its own load. It undercuts sediment banks and triggers secondary failures along its path. The larger it becomes, the more energy it carries, the faster it moves, and the harder it becomes to stop. Documented turbidity current velocities range from a few meters per second and smaller, gentler flows to over 25 meters per second, nearly 90 kilometers per hour, in the largest events. These are not estimates. They are calculations derived from the timing of cable breaks. The 1929 Grand Banks event was not a theoretical maximum. It was a measured one. Turbidity currents can travel for hundreds to thousands of kilometers across the abyssal plain before their momentum finally dissipates, and they deposit their load in the vast, flat submarine fans that form where the slope levels out into the deep. Let's go back to 1929 and reconstruct what actually happened, because it is the most complete forensic record of a turbidity current event ever assembled, and it is worth understanding in full. On November 18th, a magnitude 7.2 earthquake struck approximately 250 kilometers south of Newfoundland, beneath the Grand Banks, a region of shallow ocean sitting on a broad continental shelf, heavily loaded with sediment carried by rivers and glacial outwash over thousands of years. The earthquake destabilized an area of sediment estimated at hundreds of cubic kilometers. The slope failed. The material began to move. What followed was not an instantaneous collapse. It was a sustained, accelerating flow that moved south from the continental slope, down the gradient toward the abyssal plain, for the better part of a day. At the time, 12 transatlantic telegraph cables crossed the seafloor in that region, the communications infrastructure connecting North America to Europe, carrying the financial, diplomatic and personal communications of two continents. The northernmost cables broke first, those closest to the earthquake epicenter, and the initial slope failure, at or near the time of the earthquake itself, likely caught in the initial landslide. Then, over the following 13 hours, cables further and further south began to break, each one at a precise recorded time, each one further from the origin point, each one at greater depth as the flow moved down the slope and onto the plain. The cable engineers of 1929 knew the cables had broken. They did not know why. The breaks were documented, repair ships were dispatched, and the interruption to transatlantic communications was logged as an anomaly associated with the earthquake. The cables were repaired. The event was noted. The explanation came decades later, when oceanographers Heezen and Ewing, examining the cable break records in detail in the 1950s, laid the break times and locations against a simple velocity calculation and realized what the sequence meant. The cables had not been broken by the earthquake directly. They had been broken by something that traveled away from the earthquake at measurable, calculable speed. Something that moved from cable to cable with the consistency of a physical object in motion, decelerating slightly as the slope flattened, eventually coming to rest somewhere on the abyssal plain to the south. The telegraph network had functioned, accidentally and posthumously, as a seismograph for an event that no instrument had been designed to measure. The current deposited sediment across an estimated 160,000 square kilometers of seafloor, an area roughly the size of Tunisia, covered in a new layer of graded sediment coarser at the base where the heaviest particles settled first, finer at the top where the lightest material came to rest last. One event, one flow. One new geological layer across 250,000 square kilometers of ocean floor. Now zoom out further, from one event to millions of years of repeated events, and look at what turbidity currents have built. The Hudson Canyon begins near the mouth of the Hudson River off New York City and extends approximately 800 kilometers across the continental shelf and slope to depths exceeding 3,500 meters. It is wider in places than the Grand Canyon. It was not carved by the Hudson River. The river terminates at the coastline and has no direct mechanism for cutting a channel through hundreds of meters of underwater sediment. It was carved by repeated turbidity currents over millions of years, each one scouring the canyon walls, deepening the channel, extending the head of the canyon slightly further toward the shelf edge. The Monterey Canyon, off the coast of California, reaches depths comparable to the Grand Canyon. The Congo Canyon is connected directly to the mouth of the Congo River, one of the few submarine canyons in the world where an active river flows directly into a canyon head, maintaining a near-continuous supply of sediment that triggers turbidity currents with unusual frequency and regularity. These canyons are not curiosities. They are the superhighways of the deep ocean sediment transport system, the channels through which material from the continental land surface reaches the abyssal floor. Without them, the sediment delivered by rivers would accumulate on the continental shelf indefinitely. With them, it is periodically flushed downslope, delivered to depths of 3,000, 4,000, 5,000 meters, and deposited in the submarine fans that have built the flattest terrain on Earth. The Amazon fan extends over 700,000 square kilometers off the mouth of the Amazon River, roughly twice the area of Germany, in water depths reaching 4,000 meters and beyond. The Indus fan in the Arabian Sea covers approximately 1 million square kilometers and represents one of the thickest accumulations of submarine sediment on Earth, built over tens of millions of years of turbidity current delivery from the erosion of the Himalayan mountain range. The abyssal plain's flatness is not a geological default. It is a construction project. Millions of years of turbidity currents smoothing volcanic seafloor topography. filling in the gaps between mid-ocean ridges and seamounts, depositing layer upon layer of graded sediment until the irregular basaltic surface of the ocean crust was buried under hundreds of meters of accumulated flows. The flattest terrain on the planet was built by storms. Here is the part of this story that lands differently when you consider what the world runs on today. In 1929, the cables that broke were telegraph cables. Their loss interrupted communications for weeks and required costly repair expeditions. But the ultimate consequence was delayed messages and frustrated financiers. Today, approximately 95% of all international internet traffic, financial transactions, communications, streaming data, military communications, cloud computing services, the operational backbone of the global economy, travels through submarine fiber optic cables lying on the ocean floor. Roughly 1.3 million kilometers of cable span every ocean basin, connecting every continent except Antarctica to the global data network. These cables are thin. Most are no wider than a garden hose in deep water where abrasion and anchor damage are less likely. They lie on the seafloor, the same seafloor that turbidity currents cross at 90 kilometers per hour, that benthic storms resurface with abrasive sediment pulses, that submarine landslides redistribute across hundreds of thousands of square kilometers in a single event. In December of 2006, a magnitude 7.1 earthquake struck near Hengchun, Taiwan. The earthquake triggered turbidity currents along the Luzon Strait. Over the following hours, 9 submarine cables were severed. Internet connectivity across large parts of Southeast Asia, including the Philippines, Vietnam, Taiwan, and parts of China, was significantly degraded for several weeks while repair ships located the damage, navigated the affected terrain, and spliced new sections into the broken lines. The 1929 event reconstructed by forensic oceanography. The 2006 event experienced in real time by hundreds of millions of internet users. The ocean floor storm system is not a historical curiosity. It is an active geological process operating beneath an infrastructure that the modern world has made itself entirely dependent on, and that cannot be relocated, cannot be fully protected, and cannot be monitored at the speed and scale required to issue warnings before an event reaches its path. Cable operators route their lines to avoid the highest risk zones where they are known. They bury cables in shallow water where anchors pose the greatest danger. They maintain fleets of specialized repair ships on standby in strategic locations around the world. But turbidity currents do not follow routes that cable engineers can always anticipate. They follow gravity. They follow the geometry of underwater slopes that shift, accumulate, and fail on their own schedule, on their own terms, with no obligation to announce themselves before they move. Beneath the engineering problem is a deeper scientific one, and it is humbling in the same way that the ROV problem in the bioluminescence episode was humbling. No turbidity current of significant size has ever been directly observed from beginning to end. Not one. We have never watched a major turbidity current from initiation to deposition in real time, with instruments intact and transmitting throughout. The reasons are straightforward. The fastest, most powerful events carry abrasive sediment at velocities that destroy any instrument placed in their path. Acoustic current meters, the tools most commonly used to monitor near-bottom flows, are typically knocked over, buried, or swept away by major events. Seabed survey vessels cannot be positioned above active flows safely or with sufficient advance warning. ROVs cannot operate in sediment concentrations that blind cameras and jam propeller systems. What we have instead is forensic evidence. Sediment cores, cylindrical samples drilled vertically through the accumulated layers of the seafloor, reveal turbidite sequences, alternating bands of coarser and finer material that represent individual past events. Each turbidite preserves a characteristic internal structure, first formally described by geologist Arnold Bauma in 1962. A fining upward sequence where the coarsest, heaviest particles settle first and the finest clay-sized material settles last, creating a readable stratigraphy that documents the waning energy of the flow that deposited it. A sediment core through the right section of abyssal plain is a historical record of every major turbidity current that has crossed that location for potentially millions of years. Each layer is a separate event. Each layer's thickness is a rough proxy for the volume of sediment transported. Each layer's grain size distribution speaks to the velocity of the flow. The intervals between layers encode the recurrence frequency, how often, on geological timescales, the slope above failed and sent its load downhill. We are reading the storm archive of the ocean floor, not from direct observation, from the sediment that the storms left behind. It is oceanography doing forensics, reconstructing the physics of events no instrument survived, using the only record those events chose to leave. There is an ecological dimension to this story that sits underneath everything else and rarely receives attention. The deep abyssal floor, including the zone at 3,600 meters, is not the sterile wasteland it appears to be. It supports communities of organisms, holothurians moving slowly across the sediment surface, polychaete worms threading through the top millimeters of the seafloor, foraminiferae building their microscopic calcium carbonate shells, brittle stars extending arms across the sediment in search of food particles, occasional fish sitting motionless just above the bottom. All of them live in a food environment defined by scarcity. Marine snow arrives at this depth as a faint, intermittent trickle, a fraction of the organic production of the surface world, degraded by passage through the water column above, depleted by the communities in the mesopelagic and bathypelagic zones that intercepted it on the way down. Turbidity currents change this equation dramatically. When a turbidity current crosses the abyssal floor, it buries everything in its path under a layer of new sediment, potentially meters thick in major events. The existing benthic community is smothered. The carefully constructed spatial patterns of organisms, territories, feeding zones, accumulated over years or decades, are erased. The surface is reset to fresh, undifferentiated sediment, but that fresh sediment is loaded with organic material. The continental shelf sediment that turbidity currents transport is not geologically sterile. It is rich in organic carbon from river-delivered terrestrial material, from the productive coastal and shelf ecosystems above, from the accumulated biological matter of shallow water environments. When a turbidity current deposits its load on the abyssal floor, it delivers a pulse of nutrition to a community that normally subsists on the near-nothing that marine snow provides. The Congo Canyon is the most dramatic example. Connected directly to the Congo River, which drains one of the most biologically productive river basins on Earth. It delivers turbidity currents carrying organic material from equatorial African rainforest ecosystems directly to abyssal depths of 4,000 to 5,000 meters. The deep-sea benthic community downstream of the Congo Canyon's mouth is, in terms of organic input, one of the most generously supplied in the abyssal ocean. Turbidity currents simultaneously destroy and provision. They reset the surface, killing what was there, and replace it with enriched substrate that fuels the communities that recolonize in the aftermath. They are the deep ocean's version of the wildfire, catastrophic in the short term, generative across the longer arc. The deep ocean does not experience its geological events as purely negative. The storms that cross the abyssal floor at 3,600 meters are also, in a different timescale, a form of delivery. Here is the reframe. We have a working model of what the ocean floor is like. Still, ancient, permanent, a final resting place for sediment, for whale bones, for plastic, for everything that sinks from the world above and does not rise again. The abyssal plain reinforces this model because it looks, in photographs and maps, like exactly what stillness should look like. Flat, gray, featureless, patient. That model is wrong. The abyssal plain at 3,600 meters is not a resting place. It is a surface that gets rewritten. It is terrain shaped not by the slow accumulation of marine snow alone, but by episodic, violent, high-energy events that move more sediment in a single day than marine snow accumulates in 10,000 years at a given location. It is a floor swept by flows that travel at highway speed, carved by canyons that rival the largest geological features on the continents, built by fans so vast they are measured in hundreds of thousands of square kilometers. And it is doing all of this in darkness so complete that we have never watched it happen. The 1929 cables gave us timestamps. The sediment cores give us layers. The canyon walls give us the cumulative record of millions of years of repeated events. But the actual moment, the physics in real time, the leading edge of a turbidity, current crossing the floor at 90 kilometers per hour. The sediment cloud rising 50 meters off the bottom and advancing like a storm front through water that has never seen light. We have assembled that picture entirely from its aftermath. We know the ocean floor moves like a storm because a set of telegraph cables broke in the right order, at the right times, in 1929, and some careful scientists decades later had the insight to read the pattern. The ocean told us what it does once. Using equipment we put there for a completely different purpose, and we were paying enough attention to eventually hear it. That is the story of the deep ocean in miniature, a system operating on its own schedule by its own rules at scales and speeds that our instruments barely catch, leaving evidence in places we weren't looking for it and giving up its secrets only when we ask the right question of the right data. The floor moves. The storms are real. The archive is in the sediment. We just have to keep reading it. This series has now mapped the ocean from 400 meters to 500 meters. The twilight zone, where light dyes the midnight zone, where bioluminescence became a weapons system. The upper abyssal plain, where underwater storms reshaped the largest terrain on Earth. And the hadal depths, where plastic has become geological record. At every depth, the same lesson. The deep ocean is not a passive backdrop. It is an active system. It has weather. It has ecology. It has chemistry, physics, and biological arms races operating on timescales and at scales that dwarf anything we experience at the surface. Next episode, we are finally going to the place promised 2 episodes ago, the place that breaks the most foundational assumption in all of biology: hydrothermal vents. Cracks in the seafloor where water heated to over 400 degrees Celsius erupts into the near-freezing abyss, carrying a cargo of dissolved minerals and chemical energy. And around those cracks, tube worms 2 meters tall, ghostly crabs, dense mats of chemosynthetic bacteria, entire ecosystems operating with zero input from sunlight, zero connection to the biological pump, zero dependence on the surface world. Life that runs entirely on the chemistry of the Earth itself. It does not need the sun. It never did. It sounds impossible. It is one of the most important discoveries in the history of biology. Hit like and subscribe. We are going there next.